Hi everyone, I am Tetsushi Ikeda, a master student at Tohoku University, Japan. Actually, I am very nervous now because this is my first time to have a conference presentation in my life. So I will do my best. And thank you. Anyway, let me start my presentation on LoopBot, representing continuous haptics of grounded objects in room scale VR. This work was also done by Kazuyuki Fujita, Kunpei Ogawa, Kazuki Takashima, and Yoshifumi Kitamura. So in recent years, room scale VR has been attracting attention. As this video shows, room scale VR allows the user to explore a virtual environment by physically walking through it, which produces highly immersive experience. One major problem in room scale VR is the difficulty of haptic representation. In particular, it is quite difficult to represent haptics for large grounded objects such as walls, tables, and handrails, because the haptic object is spread over a wide area. One solution to this is to place all passive haptic props as in the left figure, or to ask people to manually place the props as in the right video. However, these approaches are costly and clearly impractical. Accordingly, researchers have explored encounter-type haptic devices, which provide haptic feedback to the user at appropriate locations and times. Previous studies, Zoom Walls and RoomShift, developed encounter-type haptic devices using multiple hoiled robots. As shown in this video, these devices achieve haptic representation of large grounded objects. However, their limitation is that the system tends to be complex as they need to manage multiple robots around the user, which increases placement delays and collision risk. To overcome this limitation, we focus on the use of looped haptic props. Several previous studies have considered special haptic mechanisms that represent objects of unlimited length by rotating or scrolling a circular haptic prop in response to user motion, as shown in this video. This idea has only been considered for fingertip haptics, but we believe that it can also be applied to haptics in room scale VR. Therefore, we propose LoopBot, a novel technique to provide continuous haptic feedback with a single robot and scrolling prop. To explain the key idea of LoopBot, let us consider reproducing the haptic feedback when the user walks while touching a wall. LoopBot has a haptic prop mounted on a horizontal robot, and the robot follows the user while the prop scrolls to cancel the robot's movement. This combination allows the prop to behave as if it were stationary. For example, if we consider a point A on the wall, the absolute position of A is maintained even if the robot moves. This allows the user to perceive the object as grounded. To prove this concept, we developed a prototype that replicates the experience of walking while holding a handrail. This is the overview of the prototype. We use an omnidirectional robot to enable quick movement of the haptic prop to any position. The prop scrolling is achieved by rotating the two drive shafts, one of which is driven by a stepper motor. The position and orientation of the prop is detected by the two vibe trackers mounted on the robot. In addition, we place two protective panels which prevent the user's hand from getting caught in the rotating pulley when holding the prop. The figure shows the system workflow of how to operate the robot. First, the system obtains the position of the user's HMD and the robot. Based on this, the system determines the target position of the robot so that it can represent haptics of the handrail closest the user. The velocity of the robot is determined using PID control, calculated at 10 Hz. At the same time, based on the robot's velocity, the system set the rotation amount of the stepper motor to be equal to the value of the robot's movement distance at each period, 10 Hz. Communication from Unity to the robot and the stepper motor is done via Bluetooth. This video shows the behavior of the prop from the top view. Please take a look at the LED sign attached to the prop. As you can see, the absolute position of the LED sign is generally maintained, even though the robot speed changes depending on the user's position. And this video shows an example of the user experience using the prototype. In VR, the user is walking down a straight corridor while holding a handrail. You can see that the system is able to provide the haptic feedback of an infinite length of handrail, as long as there is room for the robot to run. As a performance test of the prototype, we evaluated the prop's motion cancelling ratio, which means how much the prop's motion can be cancelled compared to a conventional user-following robot. We calculated this by dividing the velocity of the prop with the scrolling function by that without the scrolling function. This video shows how we measure these velocities. We attached an additional vibe tracker on the looped prop and measured these positions to calculate velocities. The obtained results show that the motion cancelling ratio was 77.5%. This graph shows the obtained time series changes of the robot's velocity relative to the ground for 3 sample trials. The orange lines show the velocity without scroll, and the blue lines show that with scroll. For the blue lines, a velocity value closer to 0 indicates a more successful cancellation of the robot's motion. From this graph, we can observe that the robot's movement was generally cancelled by our scrolling function successfully. We can also observe that the prop responded overly to the robot's motion when it started to accelerate and decelerate. But it could be corrected by adjusting the PID parameters. Next, we conducted a preliminary user test to examine the user experience with our prototype. In this test, participants were asked to walk along a corridor for 7 meters with and without our subjective comment. Our prop scoring function. For each trial, we obtained the subjective realism of the experience and the sense of the groundedness of the handrail, as well as the subjective comments. 10 people participated in the test. Here are 2 videos showing the 2 conditions used in this test. So the with scroll condition is our proposal. And the without scroll condition replicated the haptic feedback provided by a conventional user-following robot where the scrolling function was disabled. Here are the results of the subjective scores on the 2 metrics. The blue bar shows the with scroll condition, and the orange bar shows the without scroll condition. The results show that the scores for the with scroll condition were significantly higher on the both metrics, showing that our scrolling function produces a higher realism of the experience and higher sense of groundedness of the handrail. Regarding subjective comments, most participants prefer the experience with scroll. They mentioned the sense of grasping an actual handrail, the handrail being grounded, and the enhanced immersion. These comments indicate that the prototype is adequate to allow user to perceive as grasping a grounded handrail. On the other hand, there were also comments on improvements. For example, many participants complained that the driving sound from the robot decreased the margin, and that the haptic firmness of the handrail differed from what they had visually expected. These points should be considered in our future exploration. Let us mention our future direction of this study. We only demonstrated our technique in a scenario of straight walking while grasping a handrail. But many other application scenarios can be considered. First, we would like to try representing curved paths. This can be achieved by dynamically changing the robot's orientation according to the path, or using visual haptic redirection. Second, we will also explore representing flat surfaces, which could be used to create walls and tables with infinite lengths. Third, our technique will be able to represent relative velocities of the haptic objects, not only grounded objects. For example, this could be used to represent the change in relative velocity of the handrail when riding on a moving walkway. Finally, we also need to deal with the risks of the robot fall in case the user leaned on it. For this, we consider using other visual metaphors other than a handrail or adding physical supports of the robot to increase its durability. So this is a summary of this talk. Thank you for your attention.
Thank you for the great talk. We'll take one quick question, if you have any. I have a question. Have you considered any rendering multiple sensations?
Multiple sensations?
Yes.
Right
now you have only one solid feedback. Have you considered any different types of sensations?
Yeah. I consider the multiple sensation is, for example,
like soft, rough, or
okay, I see. The texture of the prop is can be changed by the for example taping something or something, but change of texture is have impact on the friction. The friction is used for prop scoring. So we have to explore that things.
Okay. All right. Okay. Thank you so much. Let's give a round of applause. We